Hello everyone. In the previous videos, we have discussed about substitution theorem. Before that, almost we have covered all the theorems in the previous videos. So last video we have discussed about substitution theorem. Okay. In this class, we are going to discuss about Tellegen's theorem. So at the end of this video, student will be able to state the Tellegen's theorem, explain this Tellegen's theorem, and apply the Tellegen's theorem to the electrical circuits. Okay, these are the outcomes of this stuff. Now we'll see the what we have discussed already, that is substitution theorem. Before that, already we have taken almost all theorems. These are the outcomes also we have taken, objectives, and finally we'll be getting, that is at the end of this, these are called outcomes: state, explain, and all three. Okay. Now we know already few things. Unknown is Tellegen's, right? Tellegen's theorem. That we have to find from the known values. That is only from known to unknown. So these things already we have taken. Many laws and theorems are available for solving networks. Like some only I mentioned here: KCL, Kirchhoff laws, KCL, KVL, Maxwell's loop current method, nodal analysis, superposition, Thevenin and Norton's, even substitution, maximum power transfer theorem, etc. Almost all the theorems also we know now, right? Already we have discussed those things. Now this is also one of such theorems. Tellegen's theorem also one of that. Now what it states? Statement, right? That is our first part. Tellegen's theorem states that summation of instantaneous power for n number of branches in an electrical network is 0. Simply summation of powers is equal to 0. That is a simple meaning of this. Summation of instantaneous powers for number of branches is equal to 0. Same we can give by using another statement. Tellegen's theorem can also be stated in another sentence as: in any linear, even this is also applicable for the nonlinear at that time, passive, active, time variant and time invariant networks, all the cases we can use this theorem. So summation of power, that power it may be instantaneous or complex power of sources is 0. In this way also, in the first statement, in simple manner, sum of the instantaneous powers is equal to 0. Here elaborate, that is only another statement, okay, given by the scientist. Now you see here, Tellegen's theorem is independent of the network elements. Thus, it is applicable for any lumped systems that has linear, passive, active, and variant and time invariant elements. Because already we told, so this is applicable for the linear, time invariant, and variant, active and passive elements also in that. So this theorem we can use for any lumped systems. Now, and also this theorem is convenient for the network which follows the KCL and KVL, Kirchhoff's laws. Okay, this is also convenient for the network which follows the KCL and KVL. It is mainly applicable for designing filters in signal processing, particularly signal processing applications. The design at that time, this Tellegen's theorem is very important. It is also used in complex operating systems for regulating stability. But this is a very important for the different applications, particularly here. designing the filters, and also using the complex operating systems for regulating the stability. And also it is mostly used in the chemical and biological systems and for finding the dynamic behavior of the physical network. Okay, so that's the reason this is applications also. Many applications are there for the Tellegen theorem. Now, how it is, we'll see the explanation of Tellegen theorem. Simply, it is a meaning is summation of powers is equal to 0 in simple manner. Okay, if you are asking statement, you need to write elaborated that. In simple manner, summation of powers. So, summation of power means what? Product of voltage and current. All the branches you have to take, that should be equal to 0. That is the meaning of this. Now you see, already you have taken Tellegen's theorem can also be stated in another sentence. Already you have taken that, right? So that is again I mentioned here. So sum of the powers, instantaneous or complex powers, is 0. Now for the kth branch, this theorem, that is the expression it gives. Summation of this power, this is P, right? Simply saying here, it is a sum of Pk. If you are taking that is K, this is Pk. That is equal. Okay. Sum of Pk, that is equal to sigma. Sigma means sum, right? K equal to 1 to n number of branches. Product of V and K. V and I, because power is product of voltage and current. Vk and so where V is the voltage, I is the current, K is the branches, number of branches. You see here, N is the number of branches. Okay, N number of branches are there here. K equal to 1 to N, that means N number of branches. Vk is the voltage in that particular branch. If it is K equal to 1, that is the first branch. K equal to 2, that is second branch, and so on up to N branches. And current Ik is, if it is K equal to 1, that is the first branch current. If it is 2, that is second branch current. Okay. Now we'll see how it is. Let IPK, IPQ equal to IK. We assume that one. First, let us take equation 1 shows that kth branch current through the particular branch. Vk is the voltage drop in that branch. After knowing these two, Vk and Ik, but Ik is nothing but it is a IPQ. You are taking here, you are considering that. So what is the product here? Because here we have mentioned K, capital K here, Vp minus Vq, because voltage between these two. Now let's see here where Vp is, that is also voltage, this is also voltage, but different node voltages at P node and Q node. Vp and Vq are respective node voltages at P and Q nodes. Okay. Now the product here, you see here in this figure, if you observe this figure, this is one node, P node, and this is the Q node. At this node, what is the voltage? Vp. And this node, this is Vq. So how much current here it is? That is Vp minus Vq by branch resistance. In this way you have to find out. Already we used it in the nodal analysis. Same way only how to find out. Vp minus Vq by that resistance, how much it is. So that is the current IPQ. Okay. Now This is the expression for this. You see here, because we are finding the product, we know the voltage and current. So in this branch, how much voltage it is? Vp minus Vq, because we are taking Vk here, Vk, Ik, right? What is Ik here? I peak between two nodes. That's the reason P and Q nodes. P and Q here. Okay, that's the reason you are taking these two nodes. Vk, I, Vq. That is equal to, what is Vk? Again, this is Vk. Not this one. It is a Vk. So okay, Vk, I, Vq. So Vp minus Vq into IPQ. Ik is nothing but IPQ, right? So that is equal to Vk IQ. Vk. Now you see here, same you can represent here in this. That is in reverse order. Vk Ik equal to in this. That is from left to right, right to right. Right? You can see that. So Vk Ik is equal to Vq minus Vp into IPQ. Same thing if I am taking ulta, that is just a reverse of that. Now, what is IPQ here? This is when you are writing this one, this, when you are taking IQP, it is taking, that is IQP. It is nothing but what? Because actually we know the current here in this direction, P to Q. Now it is QP, that is a Q to P. So that means it is a negative direction, negative of I PQ. That is the meaning of this. This is current. You can see here. IQP is equal to minus IPQ. Because opposite direction. That is the meaning here. It is negative. We are keeping opposite direction of current. Now, after taking these two equations, that is a second equation and third equations, we will get the expression just summing both. What you will get, first one also Vk Ik, second one also Vk Ik, right? So V 2 times Vk Ik plus Vk Ik, 2 times Vk Ik, that is equal to, first one already we know, Vpq, right? That is a Vk is equal to what? Vp minus Vq into IPQ. And second, that is third equation, is Vq minus Vp into IPQ. So then again you take Vk IQ equal to 1 over 2 into that product. Same product only here. Whatever the value here, so just this value it should come this side. Okay. Such equations can be written for every branch of the network. In that way, you have to find out the values for all each and every branch. If you have a number of branches, suppose for example 3 branches, you have to write 3 equations. Assuming n branches, the equations will be n equations. That is only here. Sigma k equal to 1 to n, Vk k equal to this of. So first one, because why you are taken, one is a P, another one is Q node. That's the reason two sums here. That's the reason here. This value when you are taking this one, so sigma P and sigma, that is a Q. P equal to 1 to n and Q equal to 1 to n. Same one product we are taking here, Vp minus Vq into, both are same, only current reverse only. Okay, so first one, if you are taking this one, sigma Vp into IPQ. First we are taking only voltage and then we are applying for this, minus again we are taking sigma Vq in this case into sigma IPQ. Just expansion of that. Then after according to the KCL, algebraic sum of the currents at particular node, each node we can say is equal to 0. Already we know the KCL. What KCL says, sum of the entering currents is equal to sum of the leaving currents at particular node, right? Same thing only here. So here also we are taking two different nodes, right? A number of branches you are taking at particular node. So you have to see those currents, sum of the currents equal to 0 or entering currents equal to leaving currents. Okay. So therefore, so that current, some of these values are 0. Both the currents, if you are taking a particular node, summation of algebraic sum of the currents at each node should be, if you are taking particular node P, so that value is 0. If you are taking Q, at that value also sum of the currents equal to 0. After, so what you will get? Sigma Vk Ik equal to 0. Finally, you will get the expression, that is sigma Vk Ik is equal to 0. You see here, this is the expression. That's the reason this theorem states that just summation of which one? Instantaneous powers is equal to 0. That is only here. Sum of the instantaneous powers. Power means product of voltage and current is equal to 0. This is the explanation of which one? Tellegen's theorem. So it observed that sum of the power delivered to a closed network is 0. Entire network, if you are taking total, it is sum, right? That is equal to 0. Okay. So this proves the Tellegen's theorem and also proves the conservation of power in any electrical network. Because here power, each and every branch you are finding powers and then you are taking summation, right? Each and every branch you are taking individually and then finally you are taking sum of that, you need to get 0. That is the meaning of this theorem. Now we will see. So it is also evident that sum of the power delivered to the network by independent source is equal to the sum of the power absorbed by all the passive elements of the network. That is also because power delivered by the network means from the sources. So that is equal to absorbed power. That means which one is absorbing. So these are the passive elements, right? Like resistor, capacitor, and all. So those elements only will absorb. So that power, sum of that power is equal to this. Same like KCL, we are taking a similar way here. That is a, it is not only current, but here it is a power. Power delivered, sum of the power delivered is equal to sum of the power absorbed. Okay. Here we need to take note. It depends on voltage and current product of element, but not on the type of element. Which type it is not important. Here only important. So only product of voltage and current. While verifying the Tellegen's theorem, do not disturb original network. You should not change like other theorems what we are taking, replacing just this one and that one. But here you should not replace or you should add whatever the actual network it is there. You need to keep same network. You should not disturb that one. These two things we need to remember while solving this problem. Okay, because it is not depending upon element, it is depending on voltage and current product. And second one is you should not disturb the network, original network. Now we will take one example here. First, before going, we will take few steps for solving networks using Tellegen's theorem. So first step is, in order to justify this theorem, in electrical network, first step to find the branch voltage drops. You have to find the branch voltages. And second, you have to find the currents, branch current corresponding to the particular branch by using any conventional method. And then find the product. That is the third step. So that is only here, right? Telegen's theorem can then be justified by summing of all the products. We are finding voltage and then current, particular branch. Product of voltage and current is power, right? Summing of all these powers, that is equal to 0. That is only this theorem states. Now we'll see one example here. Okay, that is again sigma VBIP. Already we have taken. Now what you are taking, if the set of voltages and currents is taken already at particular branch B, corresponding to different instants of time T1 and T2, then Tellegen theorem is also applicable when we get the equation as shown below. That is also here. Because already at particular branch, whatever you are taking, some branches B, you are taking here. So B2, so on 3 to 4, whatever it is. Okay. So different instants of time, particular instant you will get, and another instant you are finding. So that is on VB of T1 and IB of T2. So that is the thing here you are finding. At particular branch, voltage at T1 time and current at T2 time. That product also you are taking. So that's the reason this is very important for the different types of applications. Indeed, this is very useful theorem. Okay, now we'll see one example here. Verify the Tellegen theorem for the given circuit. This is the one electrical circuit given two sources. One is the voltage source, another one is current source with one resistance. Now we should not disturb this one. Only thing is you have to find the voltages and currents each branch and then product. After finding the product, just see the summation. If the current flows from plus to minus, then treat it as power absorption. If the current flows from minus to plus, then treat it as power delivery. That is for your understanding in what way you are taking. That is, you take positive, that is from plus to minus, treat it as power absorption, and second one it is power delivery. Okay, that is from sources will deliver and others it will absorb. That is the meaning of this. Okay, now you see individual cases. Already power source it is given 10 volts. This is the 10 volts. Okay, this is the current. This is the 2 amps currents. Now this is the which one? 10 ohms. How much current it is flowing? These are the two parallel branches. You can find out and just multiply. It is not like that. How much current it is flowing here? You see here 2 amps current is flowing here. 1 amp flowing here. Another one is flowing here. Because 1 plus 1 only, that is 2. You can see in this example here. So 2 amps current it is, because these two are parallel, right? Either this one or this one. So voltage is same for all the branches. This is a 10 volts and this one also 10. Okay. How much resistance will you get here? 10 by 5 actually, if you want to find. But no need to find out the resistance here. And this branch, this is the entire branch. You can take here, this is current, right? You take this one as a current node. And here, whatever the value you are taking, this is. And second right hand side, if you are taking this, you can see this is 2. And how it is? This one. Another one is this, in this direction. Okay. So this is 2. It is splitting here 1. Because this one it is given 10 volts. And this it must be 10 volts only. So already ohms is 10 ohms. Product, it is a V equal to IR. I, how much it is? we already know 10. 10 by 10 is 1. That is a 1 amp. This is 1 amp. And here also it is another amp. In this way, first we have to find the current, because these are parallel branches. After finding the current, now we got this current and this current also. So in all the branches we have currents now. So we know the current and already we know the voltage. Here also we know the current and voltage, current and voltage. Here also actually we know the voltage and now we found the current in each and every branch. Now individually you have to take here V10, so 10 volts here. So what is the power here? V into I, product, right? So 10 into 1, that is first one. That is only observed. You can see here. And second, you see, what is second? V to A. V to A, this one. It is only delivering here. It is only delivering. Just see, that's the reason I have given this statement. So wherever it is directions plus 2, minus 2 plus and plus 2 minus in this direction. And that is a 10 into which one it is? Already it is this one. This is 10 into 2. That is a power delivery. Again find out this one. P power in the resistor, this one 10 ohms. That is the third one. Just to see this time what you will get. So V is 10, again 1. So 10 into 1 is again 10. Just you see here sum of the observed power 10 plus 10, that is equal to delivered power. That is also you can write, or so summation of 20 this power of delivered power minus 10 minus 10, how much you will get? 0 only. That is also you can take. Okay, that is delivered is equal to sum of the observed powers, or you can take sum of the all the powers. You can take 20 minus 10 minus 10. So how much will get? Already we know Tellegen theorem. So sum of the algebraic sum of the instantaneous powers should be 0. That is only the statement. So it's proved, right? So you can take that also. Power delivered is equal to power observed, because delivered is 20 here, but observed 10 plus 10. Two elements are there here, so these two 10 plus 2. Okay? That is a Tellegen's theorem is verified. We'll see another example here. You can see many number of voltage sources are there here. Sorry, one source, and but how many elements are there here? 1, 2, 3, 4, 5 resistors are there. In all the cases, just you should not disturb this network. You have to find only values, that is a power values, and then find out sum of the instantaneous powers. I'm not touching anything, just only saying that using this, just finding the currents by using KCL and KVL. You can take which one if you want. Based on that, you have to find the, if you want to find the voltages, you have to go for the node voltages, that is KCL. If you want to go for this, you can go for the KVL. That way also you can find the currents here. Okay, then by using this, so Tellegen's theorem, simply finding the values. For example, here I am taking in this figure, just for your understanding, we are taking this. This is our values only. There is no fix. We are taking V1 is 7, V2 is 2 volts. All are volts only. 7, 2, and this is 3. But it is one loop, right? This is one loop. Which one you are taking in this? When it is this one, but we don't know the value of this, how much it should be, because entire value whatever you are taking, that is also in this way. That is, if it is 7, 2 plus 3, another one is which one? So remaining value 2 plus 3, 5, remaining is 2 only. That is the voltage here. Simple way if you are taking that also. Okay? If you are taking this entire. Now we got this one, and then you can find out this one. You can see what are the value. These two are parallel branches, same value it should be here. You can see that is also. V4 is 2. When it is V4, automatically V6 also 2 only. Just you see, this is also 2. These two are parallel branches. Now after finding this one, you can see this one also, these two are parallel. V3, it should be whatever the value. If it is 3, it is also 3. Now we got the values of voltage. Then find out the currents by using KCL. At particular nodes you can take. Already I mentioned here only. This is I2, I3, I4 like that. Right? All the values you are taken. And if you are taking particular branch or node, so this current is equal to this plus this. This current at particular B node, if you are taking, this is incoming, this is outgoing. Okay, and this one, how much it is flowing here? You have to see. Just you see that one. At particular B, here, this is B. At particular B, how much it is? Is the I1 current. If you are assuming, if you are taking that one, I 5 amps, then required current I2, because these two are in opposite directions. When you are taking opposite direction, it is minus of I1. That is a 5. If you are taking I3 in this direction, I5, you see here, both are opposite direction here. You see here in this is the plus minus. Minus plus, here it is plus minus. This way it is. It is in this direction, it is opposite direction. Whatever the value you get, if you are taking this one, it is 3, opposite value, you will get another value. That is opposite of that. So similar way you can find at particular node I4, this is a D node. At this time, how much value? How to find out at particular node sum of the all the currents and then find out the current value. Okay, just apply KCL. I am not calculating here, just to find out the values based on this. For your understanding, just don't touch. That is a don't disturb any curve. Just to find out by using KCL, find out the currents here, and by using KVL, find out voltages. Or you can take, if you want that, you can use another method by applying the loop analysis. You can find the which one? You can find the currents by using loop analysis, or here also if you are taking this one, how much current, here you find out another. Then after solving those three equations, because three loops are there here, it is one loop, this is another loop, and this is another loop. So three loops, and then solve these three, you will get the currents. And then see here how much current here. So difference between these two, right? So how much current here, and here also difference between this. Here it is same. So in this way you can find the currents. And then if you want to find out voltages, you can select here how much voltage at this node, and then this node, and then particular node here. All the nodes B, C, D, F, you can find the values of voltage. After finding the values of voltage and current, then use this one, because summation of voltage and current, it is equal to 0. That is only Tellegen's theorem states that. We can use this one, we can find out the value. Okay, just this is after finding the values voltage and current, just sum of this one, because we have total 5 here. You can take 1, 2, 3, 4, 5, 6 total. Because you see 1, 2, 3, 4, 5, these are common, right? So this one total 6 nodes. So 6 we can here this is one branch, second branch, third, fourth, fifth, sixth, total 6 branches. That is the meaning. Okay, number of branches. This one it is number of branches. 6 branches. Sum of this equal to 0. So that means it is a proof. Okay. So applications also already we have discussed these applications. Digital signal processing and all, especially just biological and chemical process, even for the topology, structure of reactor, network analysis, and also chemical plants also used to build complex circuits for finding the stability. So this is a very important theorem, particularly in different applications. Okay, till now we have discussed about Tellegen theorem statement, explanation of Tellegen's theorem, and also apply, that is the application of Tellegen's theorem, the electrical circuits. Thank you.